Good morning. I'm Shilpa.Chippalakatti, working as an assistant professor in Department of Electronics and Communication Engineering, Sir M. Visvesvaraya Institute of Technology. I'm a research scholar under Visvesvaraya Technological University, Bangalore, Karnataka. Today, I'm going to give a presentation on identification and segmentation of tumor using a deep learning and image segmentation algorithms. These are the table of contents. I'll be discussing about introduction, literature survey, objective of the paper, method and implementation, results, discussion, conclusion, and references. Introduction. Many diverse cognitive, sensory, and motor processes that are essential to human life and experience are done by human brain, an incredibly complicated and complex organ. Cells have a natural ability to multiply, grow, and divide to create new cells, tissues. Certain external factors can disrupt this balance, leading to the uncontrolled cell growth and formation of tumors. The rising mortality rates in the infants and adults, and specifically in the elderly, is due to the existence of tumor. As claimed by the Globocon, the brain tumor cases was 3,08,102 and 2.5% of people dead with tumors. Tumors are of two types, benign tumor, which are non-cancerous, and malignant tumor, which are cancerous cells. Early detection of the tumor is very important to decrease the mortality rate, and manual detection is very tedious, time-consuming, and requires expertise in it. So, automated methods are utilized for detection of a tumor. DL techniques are more explored by the researcher due to its fast and accurate detection rate. You only look once. YOLO algorithm is one of a DL technique which is used for the brain tumor detection. Hospitals store patients' information in the cloud to maintain the patient's medical history. Continuous storage of all the medical data into the cloud may increase the storage cost. Image segmentation might be used to effectively reduce the cloud storage space of the medical images. These are some of the literature surveys which we have gone through. The researcher in 16 have used YOLO V2 Inception V3 model for tumor localization, and they have got a prediction higher than 0.90. The researcher in 18 have used YOLO V3 model for tumor localization. They have used a DICOM dataset which consists of 1,000 images, and they have got an accuracy of 81.9% on a training data set and 94.3% on the testing data set. Researcher in 19 have used YOLO V4 small model for the tumor identification. They have taken a data set from the Figshare data repository. The model had a precision value of 0.8074 without processing, and the processed data gave a more precision value. The researcher in 20 used YOLO V5 training V5 model for a tumor segmentation purpose. They have used a BRATS 2018 dataset, which incorporated 1,992 images, and they have got a precision value of 85.95%. The researcher in 22 have used YOLO V7 model for the accurate detection of the meningliomas, gliomas, and pituitary gland tumors. The model utilizes a publicly available dataset comprising of 2,548 images of gliomas, 2,658 images of pituitary tumors, 2,582 images of meningiomas and 2,500 images of non-tumor cases for training purposes. To enhance the YOLO V7 feature extraction capabilities, the convolutional block attention model is incorporated, focusing on silent regions associated with the brain cancer. Additionally, the model integrates the spatial pyramid pooling fast plus layer into its fundamental architecture to enhance the sensitivity. Further, the bidirectional feature pyramid network is employed for multi-scale feature fusion, efficiently capturing the tumor-relevant information. The researcher in 23 have used YOLO V8 algorithm along with the data augmentation, which can detect the brain tumor. They have used uh, T1 weighted contrast enhanced image dataset, which consists of 3061 images in it. The data augmentation, which was implemented along with it, was like flip, 90-degree rotate, crop, rotation, then share, grayscale, brightness, exposure, blur, and noise is applied to it. The model performs better with the augmentation, yielding a precision of 0.942, recall of 0.908, MAP 50 as 0.952, and MAP 5095 as 0.733. The researcher in 24 have used a tumor YOLO V8 for the tumor detection on the open source data set. And they have also used an data augmentation techniques like 90-degree clockwise, 90-degree counterclockwise, and upside down has been applied. So the model gave a precision value of 0.943, recall of 0.932, MAP 50 of 0.941, specificity of 0.938, MAP 5095 as 0.4421. Researcher in 26 have used an additional model along with the YOLO V8N model to enhance the performance. The additional model is a diet that is a data efficient image transfer model, and the vision transformer model is used from a fine-tuned ResNet 152 is incorporated along with the YOLO V8 to enhance the performance. The data set was taken from the National Brain Mapping Lab, which comprises of 81 patients, of which 30 are tumor and 51 were normal cases. The researcher in 27 have used photoacoustic imaging instead of the MRI images. They have used a photoacoustic image for the detection of a tumor. The researcher in 28 have used advanced lesion detection model. DHC YOLO is proposed, which integrates a multi-scale dilated attention and multi-head self-attention within the YOLO V8 network. It also adds a feature pyramid network for enhanced features. This model is tested against the brain tumor, colonic polyp, and the esophageal cancer dataset. The brain tumor dataset achieved an accuracy of 88.3%. From the literature survey, it is clear that compared to other YOLO model, YOLO V8 can give better performance, but performance of the YOLO V8 model can still be enhanced to get the precise detection. As well as the researcher has only concentrated on the tumor detection and localization, but storing the huge amount of data with the reduced cost is not being taken into consideration. So in our proposed model, we are going to explore the YOLO V8 model for the brain cancer detection and segment the infected area using the image segmentation algorithm. The segmented image will be saved in the cloud using the patient ID and location of the image to save the cloud space, and in turn cost of the storage will be reduced. The performance of the model is evaluated based on the data set used, number of epochs it takes, precision, recall, MAP 50 and MAP 5095, and the image size after segmentation. Let's discuss about the methods and implementation, how we have done. So this figure 1 shows the block diagram of a brain tumor detection using a YOLO V8S model. So the first block shows the we have collected a data set from the open source data set, and the MRI images is given as a input to the model. And the first stage in the model is pre-processing stage, where we are going to resize the image, grayscale conversion is going to happen, and the data augmentation is performed on it. And next stage is after doing this pre-processing stage, next is a model training. Before model training, the data is split into the training, testing, and validation, which is in the ratio of 71 is to 19 is to 10. And then it is given for a model training purpose. And once the model training is done, a model testing will be performed on the model. After the detection, the tumor segmentation is done using the image segmentation algorithm. The segmented image is saved in the cloud using the patient ID and the location of the tumor. So these are the different methods by which we are going to implement it. So first we have used an MRI image. Why we have used an MRI image? It is a non-invasive imaging technology capable of generating a detailed three-dimensional anatomical images commonly employed for disease detection, diagnosis, treatment, and monitoring. For that purpose, we have used an MRI image in our studies. So the data set used, the data set which we have used is an open source data set which consists of 639 images of tumorous, non-tumorous, meningioma, glioma, and pituitary. For training, the data set split into training, validation, and testing. In our data set, we have taken 453 images for training, 122 images for validation, and 64 images for testing in a ratio of 71 is to 19 is to 10. The image size is taken as 640 cross 640. On the dataset, image processing like data conversion to suit the format of YOLO V8S, removing repeated images, resizing the images, and grayscale conversion is applied using the Roboflow application. Next stage we have taken is data augmentation. Data augmentation method, it is used to enlarge the size of the data artificially and to create a new data set within the existing one. The approaches such as noise addition, data rotation, and scaling intentionally augment the data set size. In the proposed model, the data rotation minus 15 degree to plus 15 degree, grayscale up to 15%, and noise addition techniques are used to augment the data. About the YOLO V8 model, it is a most recent and the advanced YOLO model. It is applicable to the task including instance segmentation, object identification, and picture classification. Keeping the general structure as YOLO V5, YOLO V8 makes a modification in the CSP layer, which is also called as the C2F model. Cross-stage partial bottleneck with the two convolutions. As this model is shortly called, it efficiently combines the contextual information with a high-level characteristic to increase the detection accuracy. By enabling each branch to concentrate on its specific task, the anchor-free model of the YOLO V8 with a decoupled head enhances overall accuracy by independently handling regression, task, objectness, and classification. Figure 2 shows the detailed YOLO V8 architecture, where we can see that we have a CBS layer as well as a C2F layers. The performance evaluation. The performance of the model is being evaluated by using these parameters such as the confusion matrix, precision, recall, MAP50, MAP50 95. Confusion matrix, after training a model, validation of a prototype is performed using a confusion matrix. It contains true positive in which the model precisely predicts a label that is consistent with the reality. False positive even indicate that the prototype has predicted a label that wasn't in the ground truth. Precession. The precession is a measure that expresses the percentage of accurate production within the total number of productions and is utilized to access how accurately the system responds to the user request. Precession is calculated by a formula as true positive divided by true positive plus false positive. Recall. Recall is the amount of genuine positive to the all items. For instance, if the image had 100 trees and the model properly recognizes 75 of them, then the recall is 75%. Recall is taken as true positive divided by true positive plus false positive. Intersection over union, IOU, is a matrix used to quantify how much two bonding boxes overlap. The AOI value is the number between 0 and 1, where 0 indicates no overlap, 1 indicates perfect match or full overlap. IOU is the area of intersection divided by area of union. Mean average precession value. The average of the average precession for every class is called as a mean average precession value. The computation of the average precession involves taking recall values ranging from 0 to 1, accuracy at the 0.5 or 50%. IOU threshold is measured by the matrix MAP50. All that matters is if there is more than 50% overlap between the anticipated and the ground truth bonding boxes, the process is deemed successful. It is in a similar way, MAP 50, 95 between denotes IOU between 50 and 95. This is the formula by which we can calculate the MAP, mean average precession value. So this is a system specification. So what was our system specification? For the implementation of the model, we have used a Google Colab using a Python language. The system specification for training of the model are Ultralytics YOLO v8.0.196, Python 3.10.12 we have used, and Torch we have used is 2.3.0 plus CU121, and CPU Intel Xeon 2.20 gigahertz. So the trainer specification here, we have used an algorithm of YOLO V8S model, and image size of 640 cross 640, batch size of 16, patients 50, and the epochs is 20. Results. Let's discuss about the results. Results here, the tumor detection capability of the YOLO V8 is evaluated using a parameters like precision, recall, MAP50 and MAP5095. So the prototype was trained for 20 epoxes, taking an instance of 5, 10, 15, and 20. And here the model has 168 layers, 1112591 parameters, 0 gradient, and 28.4 GFLOPS. So here the table 2 shows the output of the output for each of the epoxes, how much is the value we have got for each of the epoxes of precision, recall, MAP50, MAP5095. So the figure 3 shows the training losses, where the 3A shows the box losses, 3B shows the CLS loss, and 3C shows the DFL loss. 3A represents the detection of the multiple objects in the image using the bonding boxes. The motto of the box loss function is to calculate the error between the predicted bonding boxes and ground truth bonding boxes. As this loss decreases over epochs, the model is going to improve its capability to accurately predict the bonding boxes. Figure 3B represents the objectness loss, which is the behavior of the objectness and the class score in the model. Objectness refers to the confidence of the model in the presence of an object within the bonding boxes, and the class score represents the conditional probability of a specific class. It is describable for the objectness to decrease towards 0 with a number of epochs as depicted in the graph. Figure 3C related to the classification. The classification has two things in it. One is to determine whether the object is in the image, and second one is to identify the class of that object. Figure 4 shows the validation losses. So here also in validation, we have 3 losses: box loss, CLS loss, and DFL loss. Figure 5A, B, C, D represents the precession recall MAP50 and MAP5095 for the training data set on the y-axis of the graph and the number of epochs on the x-axis of the graph. After the 20 epochs, the box losses which we have got is 0.6765 and CLS loss is 0.507 and DFL loss is 1.039. The figure 6 shows the precession recall curve, which gave an accuracy of almost 0.969%. And here in the figure 7, it shows the normalized confusion matrix. Figure 8, A and B shows the production as well as the tumor segmentation. Figure 8A shows the production of a YOLO V8S model, how it has produced the tumor. And after production, the image segmentation algorithm has been applied to it. And from the image segmentation algorithm, the tumor is segmented and figure 8AB represents the tumor segmented tumor image. Next one is a discussion. Let's discuss. The primary goal of this research is to detect the precise location of the tumor and further segment the infected area to save in cloud to maintain the patient's medical history. The proposed model yields 0.944 as a precession, 0.921 recall, and 0.969 MAP50 and 0.811 MAP5095 for 20 epochs on the open source data set. The data set consists of 639 images, which is split in the ratio of 71:19:10. With reference to the literature survey, the proposed model is giving better results with the open source data set. The data pre-processing is used in the model for noise reduction and data augmentation. The researcher in 23, 24, 26, 27 uses a YOLO V8 algorithm, but with a different data sets and the parameters are also different. So using the same data set, we have tested it for YOLO V5 model also. So the comparison of YOLO V5 model and YOLO V8 model for the same data set and the same parameters we have seen. So the table 3 shows the comparison of YOLO V5 model and the YOLO V8 model for the same data set what we have used. And for the same epochs also, 20 epochs only. By the table, it is clearly noted that the proposed model YOLO V8S model is giving a better results compared to YOLO V5 model. As well as in the table 4, we have shown what is the amount of memory storage required after segmentation. Before segmentation, what is the memory required, and after segmentation, what is the memory required for storing of the images. By this table 4, it is clearly noted that after segmentation, the size of the image has been reduced and the storage space is also reduced. Conclusion. The automated method for accurate detection of the tumor with less complexity and cost-effective storage of the patient medical history was needed. Our proposed model answered this issue by using the YOLO V8S model for tumor detection, and image segmentation is done to save the storage space in cloud. Open source dataset is used to test the model using 639 images, which is split in 71:19:10 across training, validation, and testing. After the 20 epochs, the proposed results were what we have got after 20 epochs was precession is 0.944, recall is 0.921, MAP50 is 0.969, MAP5095 is 0.911. The tumor is segmented using image segmentation approach, and only the region of interest is saved in the cloud, which in turn reduces the cloud storage space, which leads to the low cost storage. The image size is reduced from 28 kilobytes before segmentation to 16 kilobytes after segmentation. The future scope of this research is still more you can enhance the perfectness of brain tumor detection using the YOLO V8S model by training a model with the various kinds of data set, rebuilding of the segmented images and reducing the image reconstruction losses. These are the future scope of this paper. So these are the references which I have referred. I have referred around 29 references. Thank you.